The 3DM GX3 25 and 35, like all magnetometer-equipped inertial sensors, are subject to having their readings affected by interference from ferrous materials, materials that distort the planet's magnetic field. Ideally, the device should be mounted in a location that is distant from or free of any ferrous materials. If this is not an option, then it is key to limit interference as much as possible, and then recalibrate the device when it is finally mounted. The device's magnetic calibration can be set or field calibrated using MicroStrain's 3DM GX3 soft and hard iron calibration application. To begin calibration, connect the device and begin plotting points on the results plot. These points represent the shape of the magnetic field surrounding the device. Please note, at any time you can select the program's help feature to receive hints on what each control within the application does. If the calibration is correct, the point should define a perfect sphere, the center of which corresponds to the center of the device's reference frame. A star represents the center of the measured sphere. A circle represents the center of the device's reference frame. If there is soft iron interference, the warping of the local magnetic fields will result in the calibration points forming an ellipsoid rather than a sphere. To produce a good calibration, you should move your device to paint as much of the surface of a sphere as you can. Rotate the device and pitch, roll, and yaw. In our case, we are not restricted in our motion and can paint the outline of a complete sphere. In other applications, the mounted device's motion may be restricted and you may not be able to paint a sphere. Calibration can still be accomplished under these circumstances. After you finish plotting your data points, you can check your results by selecting either the spherical or ellipsoidal fit and zooming and panning around the 3D space of the results plot to see which fit best matches the shape of the plotted points. This demonstration shows what data collection would look like for a properly calibrated device with minimal interference. The points fit well within the spherical fit. The next demonstration shows what data collection would look like when interference, in this case a small metal clip, has been introduced to the device's local magnetic field. As you can see, the ellipsoidal fit works best. Once the fit is chosen, the user can either write the calibration to the device or save it for later use or analysis. The default factory calibration is permanently stored on the device's internal memory and can always be reset if needed. In some cases, within the context of its intended use, for instance, if the device were mounted in an automobile, rotating the device in all three dimensions may be impractical. In these cases, the same basic principles apply. Collect data while moving the vehicle throughout the maximum range of motion it will experience in actual use. Then apply a fit and either write it to the device or save it for later analysis or use. If your collected data looks more like a two-dimensional circle or ellipse than a sphere or ellipsoid, the spherical fit may be the better choice. If you are unsure, try different fits and use the one that gives you the best results in your application. It is important to understand that magnetometer calibration can only take into account static interference. In other words, it can only correct for ferrous materials that do not move relative to the mounted device. The planet's magnetic field is a valuable reference for measurement of orientation calculations. To maximize accuracy, proper mounting and calibration of the magnetometer are essential.